Hi everyone, I am Mazharul Islam, a PhD candidate at University of Wisconsin-Madison. Today I will be presenting our work titled Compact Approximating Complex Activation Functions for Secure Computation. This is a joint work with my advisor Rahul and folks from Visa Research. Cloud-hosted machine learning models can provide valuable services. For example, once trained, these models can be used for remote face authentication, performing early disease discovery from users' healthcare data, so on and so forth. However, to enjoy such services, users have to share their private data with the machine learning model. This can raise serious security concerns. For example, shared private sensitive data can be used by the ML model for training without users' explicit consent. Similarly, they could be stored insecurely and could get leaked, shared with third-party services without users' consent. One way to solve this problem is to use secure inference. In secure inference, we use multi-party computation techniques to protect users' data. Client encrypts their data before sending it to the cloud services, and at the end of the secure inference, client learns only the model output of the inference result, and cloud service learns nothing more than what is revealed by the inference result. For secure inference, we need to compute both linear operation that involves vector multiplication and nonlinear operation that involves computing the activation functions. The performance bottleneck of secure inference is computing the nonlinear activation functions. This is because MPC techniques are not specifically suitable for doing nonlinear arithmetic. As such, majority of the existing work focuses on a simple activation function called ReLU. However, there are other complex activation functions that are heavily used by the machine learning community and have compelling advantage. For example, this complex activation function can result in a model that is more robust, have better accuracy, and converges faster. There are few existing approaches. However, one question still remains how accurate and efficient these approaches are as the number of hidden layers of the machine learning model increases. More specifically, by complex activation functions, I am referring to SELU, GELU, and MISH. These functions are challenging to compute using MPC techniques because they have involved highly nonlinear math operations such as tan h of x, ln x, exponentiation of x, or inverse of x. Another challenge is small error introduced in one layer during computation can accumulate and snowball into a large error that result in a significant accuracy loss of the model. Finally, finding the appropriate parameters that are used during the approximation that is both accurate and efficient is challenging. To address these challenges, we propose Compact. Compact can generate MPC-friendly, accurate and efficient approximations of complex activation functions. It supports three popular complex activation functions: SELU, GELU, and MISH. It performs well even as the number of hidden layers increases. It is compatible with all existing MPC libraries and does not require retraining or fine-tuning the already trained model. To address these challenges, we introduce several techniques. We start by looking at the second derivative of this complex activation function. One can quickly realize that the region that is beyond -5 and +5, we can easily approximate them using two simple polynomials. Next, by focusing on the region that is close to 0, one can see that the second derivative is not flat, which implies that it's harder for us to approximate those regions accurately. We care about accurately approximating the region close to 0 because input to the activation functions are normalized and majority of the input are going to fall into the region close to 0. Next, in the approximation process, we take into account the model and the dataset. This is because one approximation that performs well on a given model and a dataset may not generalize well for other model and other datasets. Let's try to incorporate this observation into our approximation process. Say we want to approximate the region between -5 and +5 using m piecewise polynomial. Each of these polynomial can have a degree of at most k. The good thing about such piecewise polynomial based approximation is that each of these pieces is already MPC friendly. However, it is challenging to have accurate approximation that does not affect the accuracy of the final model significantly using such simple idea, especially when the number of hidden layer increases. To have accurate approximation, we use Chebyshev sequence based approximation for each of these polynomials. This is because Chebyshev outperforms spline or least square fit based approaches when the function we are approximating is complex. Next, to have accurate approximation near the region close to 0, we introduced a new way to calculate the error of the approximation function that includes the input density. As a result, the approximation process is incentivized to have accurate approximation near the region close to 0. Next, we use binary search to find the appropriate approximation error threshold. Note, increasing approximation error threshold could affect the model accuracy significantly. We could, by reducing the approximation error threshold, we could have negligible impact on the model accuracy. We find the maximum approximation error threshold using binary search such that the model accuracy is not affected significantly. Lastly, observe that finding the appropriate number of piecewise polynomial m and the degree of each of these polynomial k will be dependent on the model and the dataset. Increasing m and k will result in more accurate approximation and presumably will have negligible effect on the model accuracy. However, it might not be the most efficient approximation, resulting in high performance overhead. Decreasing m and k will have the exact opposite effect. We can pose this as a constant optimization problem, as I am going to describe in the next slide. In this constant optimization problem, we are given the model, the dataset, and the negligible accuracy loss we can tolerate for secure inference. Typically, it's in the ranges of 1%. Then we use our initial solution of m0 and k0 to generate an approximation. Once we are done, we can check if the generated approximation have negligible impact on the model accuracy. If it's not the case, then we need to increase the value of m and k to generate more accurate approximation. Once we are happy with that the generated approximation have negligible impact on the model accuracy, we can check if it's computationally efficient or not. If it's not, yes, then we are done. Otherwise, we will have to decrease the value of m and k to make it computationally efficient. As you can observe, there is a trade-off between increasing the value of m and k on the model accuracy and computational efficiency. To find the optimized value of m and k, we use a simulated annealing framework. Incorporating the simulating annealing framework to solve this constant optimization problem requires a bit more elaborate scheme, which we have described in detail in our paper, and I would be happy to talk about if you have any questions regarding that. Very briefly, here is one of our experimental results from the paper. We compare compact with other approaches to observe impact on model accuracy and inference time. We take a convolutional neural network and use the Cypher 100 dataset. Here we draw the model accuracy loss of MPC-friendly approximation using different approaches. We find that two approaches generate approximation that have negligible impact on the model accuracy, NFGen and compact. Other approaches have significant impact on the model accuracy. Then we compare compact and NFGen for computational efficiency, and we find as the number of hidden layer increases, our approach compact generates more computationally efficient approximation. In fact, for a 10-layer CNN model, our approach is about 2.9 times computationally faster than NFGen. In summary, we propose Compact, a framework that can generate MPC-friendly approximation of complex activation functions. We leverage normalization to generate density over accurate approximation. Compact dynamically searches for optimal parameters, and compact generated approximations are efficient and have negligible impact on the model accuracy as the number of hidden layers increases. Thank you all for listening to the talk. I will be online to answer any question.